Welcome to the Yawning Theories for sleepy thinkers, curious night owls, and anyone gently drifting towards dreams. You've arrived at the Yawning Theories, where the stars are vast, the questions even vaster, and the pace is calm enough not to disturb your pillow cocoon. Tonight, we embark on a tranquil journey to explore one of the most profound and enigmatic questions humanity has ever contemplated: did nothing ever exist? This isn't a hurried dash through complex equations or a frantic search for definitive answers. Instead, we'll proceed slowly with hushed voices and a gentle, open-hearted curiosity, much like drifting through a silent, star-filled night. Imagine it less as an academic lecture and more like a serene float through a galaxy of breathtaking ideas, perhaps with a warm cup of chamomile tea in hand, allowing your mind to gently wander. My sincere hope is that this video isn't too captivating, as that would be quite inconvenient if you're trying to wind down for bedtime. However, if it does manage to gently spark your mind, awakening a sense of wonder and intellectual intrigue, at least you'll be learning something truly fascinating as you slowly drift off to sleep. Before our cosmic wandering truly begins, I would be incredibly grateful if you would consider gently tapping the like button. And if you find yourself drawn to these kinds of gentle science, journeys, explorations that blend the wonders of the universe with a sense of calm and introspection, please feel free to subscribe. Your support genuinely helps more curious souls discover this peaceful corner of the internet. As you settle in, please let me know in the comments where in the world you're watching from and what time it is for you. Is it just past midnight, with the quiet hum of the night outside your window, or perhaps the early glow of 4 a.m., with the first hints of dawn appearing on the horizon? I always find immense joy in reading those sleepy check-ins, connecting with fellow seekers of knowledge across different time zones and continents. Finally, while we'll delve into some truly profound and dreamy questions tonight, touching upon the very fabric of reality and existence, please remember that this is not medical advice. It's simply intended as a soft, comforting place to land at the very end of your day, a sanctuary for your thoughts before sleep. Now, let's begin. Take a deep breath, not to immediately fill your lungs with cosmic insight, though that may come later, but simply to ground yourself in this present moment. We're about to dive into a subject that, at first glance, seems disarmingly simple. Yet, you'll quickly discover it becomes slipperier than a bar of soap in the swirling vortex of a black hole, challenging our most fundamental assumptions about reality. Tonight's core question is, what do we really mean by nothing? The concept of nothing is deceptively simple, yet it has plagued philosophers, theologians, and scientists for millennia. We use the word casually in everyday language: there's nothing in the fridge, or I have nothing to do. But when we delve deeper into its true meaning, we encounter a profound void that challenges our most fundamental understandings of existence, space, and reality itself. From a purely practical standpoint, nothing often refers to the absence of something specific. If your fridge is empty, it means there are no food items. If you have nothing to do, it implies an absence of scheduled activities or tasks. This operational definition is useful for daily communication, but it fails to address the more fundamental, metaphysical questions surrounding nothing as a standalone concept. Philosophically, the idea of absolute nothingness raises thorny paradoxes. Can nothing truly exist? If it exists, doesn't that make it something by definition? Ancient Greek philosophers, particularly Parmenides, argued that nothing could not exist because to speak of it or conceive of it would be to make it something. This led to the conclusion that all change and non-being were illusory, as only being could truly be. Later, Aristotle distinguished between different kinds of nothing, such as the absence of a particular form in matter, or the potential for something to be. Theological perspectives often grapple with the concept of creation ex nihilo, out of nothing. Many creation myths and religious narratives posit that the universe was brought into being from an initial state of absolute nothingness. This raises questions about the nature of a creator existing prior to anything else, and whether nothing, in this context, refers to a truly empty void or a state of pure potentiality. Modern science, particularly quantum physics and cosmology, has added new layers of complexity to the discussion. Classical physics largely assumed a vacuum was empty space, devoid of matter or energy. However, quantum field theory reveals that even in the deepest vacuum, there are constant fluctuations of virtual particles popping into and out of existence. This quantum foam suggests that the vacuum is not truly empty, but rather a seething cauldron of potential energy. If the universe emerged from such a state, can we truly say it came from nothing? Furthermore, the concept of nothing becomes even more challenging when considering the origin of the universe. The Big Bang Theory describes the universe expanding from an incredibly hot, dense state. But what existed before the Big Bang? Was there truly nothing, in the sense of a complete absence of space, time, and matter? Some cosmological models propose a multiverse, where our universe is just one of many, suggesting that nothing might simply be the absence of our specific universe within a larger framework. Others delve into the nature of space-time itself, questioning whether its absence constitutes nothing or merely a different topological state. Ultimately, the question of what do we really mean by nothing remains open-ended. It forces us to confront the limits of our language, our perception, and our scientific understanding. Is it an absolute void, a philosophical construct, a quantum phenomenon, or a state of potentiality? Perhaps nothing is not a singular, definable entity, but rather a concept that shifts and transforms depending on the context, a placeholder for the boundaries of our current knowledge, and a perpetual invitation for deeper inquiry into the very nature of existence. The Nature of Reality, a philosophical and scientific inquiry introduction. The question of reality has captivated human minds for millennia, serving as a cornerstone for both philosophical discourse and scientific endeavor. What is real? How do we perceive it? And to what extent does our perception shape the very fabric of existence? This inquiry delves into these profound questions, exploring the intricate interplay between philosophical contemplation and scientific investigation in our quest to understand the fundamental nature of reality. Philosophical perspectives on reality, from ancient Greek thought to modern phenomenology. Philosophers have offered diverse and often conflicting views on reality. Platonism, Plato's theory of forms, posits a realm of perfect, eternal, and unchanging forms, e.g., justice, beauty, truth, that are more real than the transient objects we perceive in the physical world. Our sensory experiences are mere shadows or imperfect copies of these ultimate realities. Idealism, particularly subjective idealism, e.g., Berkeley, argues that reality is fundamentally mental or consciousness dependent. To be is to be perceived. Objects exist only insofar as they are experienced by a mind. Materialism/physicalism. In contrast, materialism asserts that reality is fundamentally physical, composed of matter and energy, and governed by physical laws. Consciousness and mental phenomena are emergent properties of complex physical systems. Realism, naive and critical. Naive realism suggests that we perceive the world directly as it is, without distortion. Critical realism acknowledges the role of our perceptual apparatus and cognitive frameworks in shaping our experience, but still maintains that an objective reality exists independently of our minds. Phenomenology, pioneered by Husserl and Heidegger, focuses on the structure of experience and consciousness. It brackets questions of objective reality to explore the lived experience of the world as it appears to us. These philosophical frameworks provide conceptual tools to grapple with the elusive nature of reality, often highlighting the limitations of human perception and the challenges of attaining absolute knowledge. Scientific perspectives on reality science, while distinct from philosophy in its methodology, often touches upon similar ontological questions, grounding its inquiries in empirical observation and experimentation. Classical physics, Newtonian physics described a deterministic universe where reality was quantifiable, predictable, and objectively observable. Space and time were absolute, and particles had definite positions and momenta. Relativity theory Einstein's theories of special and general relativity revolutionized our understanding of space, time, and gravity. Reality, in this context, is not absolute but relative to the observer's frame of reference. Space and time are intertwined into a single continuum, space-time, which can be warped by mass and energy. This challenged the notion of a fixed objective reality that is the same for all observers. Quantum mechanics, perhaps the most profound scientific challenge to our intuitive understanding of reality, comes from quantum mechanics. At the subatomic level, particles behave in bewildering ways, exhibiting both wave and particle properties. Wave-particle duality. Key concepts include uncertainty principle Heisenberg. We cannot simultaneously know with perfect precision a particle's position and momentum. The act of measurement itself influences the reality being observed. Superposition. A quantum particle can exist in multiple states simultaneously until it is measured. Entanglement. Two or more particles can become linked in such a way that the state of one instantaneously influences the state of the others, regardless of distance. These phenomena suggest that reality at the quantum level is inherently probabilistic, non-local, and observer-dependent, leading to various interpretations, e.g., Copenhagen interpretation. Many worlds interpretation that have deep philosophical implications. Cosmology. Modern cosmology explores the origin, evolution, and large-scale structure of the universe. Concepts like the Big Bang, dark matter, and dark energy push the boundaries of our understanding of fundamental reality, raising questions about the existence of multiple universes, multiverse theory, and the ultimate fate of reality itself. Neuroscience and consciousness. The burgeoning field of neuroscience investigates the biological basis of consciousness. While still in its nascent stages, it grapples with the hard problem of consciousness, how physical processes in the brain give rise to subjective experience. This line of inquiry directly addresses the relationship between our internal mental reality and the external physical world. The interplay and convergence, the philosophical and scientific inquiries into reality, are not mutually exclusive but rather complementary. Science informs philosophy. Scientific discoveries, particularly from quantum mechanics and relativity, have forced philosophers to reevaluate traditional ontological assumptions and develop new metaphysical frameworks. The probabilistic nature of quantum reality, for instance, challenges classical notions of determinism and causality. Philosophy guides science. Philosophical questions often motivate scientific research, providing conceptual frameworks and ethical considerations for scientific exploration. The philosophical debate about the nature of time, for example, influenced Einstein's development of relativity. Emergent properties. Both fields grapple with the concept of emergent properties, how complex systems can exhibit properties not present in their individual components, e.g., consciousness emerging from brain activity or macroscopic properties emerging from quantum interactions. Conclusion: the pursuit of understanding reality is an ongoing journey that transcends disciplinary boundaries. Philosophy offers profound questions and conceptual tools, while science provides empirical evidence and testable theories. While a definitive, unified answer to the nature of reality remains elusive, the continuous dialogue between these two modes of inquiry enriches our understanding, revealing a reality that is far more intricate, dynamic, and perhaps even stranger than we could have ever imagined. The quest continues, driven by an insatiable human curiosity to unravel the deepest mysteries of existence. You'd think that of all the concepts in the universe or outside it, nothing would be the easiest to explain. After all, it's, well, nothing. No things, no stuff, just emptiness, right? But here's where it gets intriguing. The more closely we examine nothing, the more it starts to suspiciously resemble something. As we'll see, in both science and philosophy, nothing can wear quite a few disguises. In fact, there are several kinds of nothing, each stranger and more counter-intuitive than the last. The nuances of nothing. Let's start small and familiar. Picture an empty jar on your kitchen counter. You unscrew the lid and look inside. It appears empty. No peanut butter, no sugar cubes, not even a single grain of rice. Most people would call that nothing, but of course that's not quite right. The jar is full of air, oxygen, nitrogen, a bit of carbon dioxide, perhaps the lingering scent of cinnamon from whatever it held last week. Molecules are bouncing around in there like invisible popcorn. If you were an ant with a chemistry degree, you'd be overwhelmed by just how not nothing it truly is. Okay, let's raise the stakes. What if we suck all the air out of the jar, vacuum, sealing it until there's no atmosphere inside? Now we have a vacuum, or what we might call empty space. Is that nothing? We're getting closer, but even this vacuum isn't truly empty. First, there are still fields inside, not cornfields, but the invisible quantum fields that exist everywhere in the universe. According to modern physics, these can never be completely turned off. Even in their lowest energy state, they still ripple with possibility. This is where things get quantum weird. In the early 20th century, scientists like Max Planck and Werner Heisenberg discovered that nature's tiniest levels are never truly still. Even a perfect vacuum, devoid of matter and energy, is still humming with uncertainty. Tiny particles constantly pop into and out of existence. These are called virtual particles, and they are part of what physicists term quantum fluctuations. In other words, even nothing is always doing something. Imagine your empty jar again. If we could truly vacuum, seal it, remove every air molecule, and then shrink ourselves down to the quantum scale, we'd still see things happening, not because matter is leaking in, but because the fabric of the universe itself is restless. It fizzes with energy. The vacuum is like a quiet ocean that appears calm from above but teems with life beneath its surface. So here we are, two versions of nothing, down, and neither is truly empty. Let's push it further. What if we removed space itself, not just the stuff in space, but space itself? gone. No dimensions, no up or down, no left or right. Can we even imagine that? This is where language begins to fail us. Without space, we can't describe where anything is, or even where nothing could be. It's not a black void, not a white screen, not darkness, silence, or emptiness. It's the absence of place itself. You can't put your mind inside it because there's no inside. Then, let's get even more radical. What if we also took away time? No seconds ticking by, no change, no motion. A timeless, spaceless matter, less what? Some physicists and philosophers propose that this is the only true form of nothing, the absolute absence of everything, including the dimensions in which things can exist or happen. But now we're dealing with something almost paradoxical. If there's no space or time, can we even say it exists? And if it doesn't exist, then what is it? It's a bit like trying to draw a square circle. The words make sense individually, but together they become nonsense. Similarly, our brains, which evolved to track fruit, faces, and predator footprints, aren't naturally equipped to visualize the absence of all things. Nothing, in its most extreme definition, might be not just beyond our senses, but beyond thought itself. Of course, some philosophers have argued that nothing doesn't make sense at all, that it's a concept invented by language. When we say something is not there, like when your friend says there's nothing in the fridge, we still mean something. The fridge is present, just empty of the items we want. But when we talk about absolute nothingness, we're using words that point to an absence we've never encountered. Heidegger, the famously cryptic German philosopher, once asked, "Why is there something rather than nothing?" It's one of those questions that sounds obvious at first, but grows more unsettling the longer you ponder it. And the more we learn from science, the more it seems that nothing might not just be hard to find, it might not exist at all. Even the term "before the Big Bang" may already be a kind of error. If time began with the universe, then asking what came before is like asking what's north of the North Pole. The question seems to make sense, but collapses under its own logic. Still, it's a very human question. We crave origin stories. We like to trace things back. Family trees, historical timelines, the last slice of cake. But when it comes to the universe, we may hit a wall, a soft, baffling, quantum, fluctuating wall. So, in light of these recent developments and the shifting landscape, a crucial question arises. Where does that leave us? This inquiry extends beyond a simple positional statement. It probes our current standing, our potential vulnerabilities, and the strategic pathways forward. It compels us to reassess our objectives, evaluate the efficacy of our present methodologies, and anticipate the ramifications of inaction or misdirection. The implications of this question resonate across all facets of our operations, demanding a comprehensive analysis of our resources, our partnerships, and our competitive advantages. Ultimately, understanding where that leaves us is paramount to defining our next steps and ensuring our continued relevance and success in an increasingly dynamic environment. It leaves us with several kinds of nothing, all of which are actually quite something, from airless jars to seething quantum vacuums to theoretical voids outside of space and time. Nothing is not one neat concept. It's a spectrum of increasingly abstract possibilities. And in the end, we might have to accept that pure, total nothingness may not be part of reality at all, only part of our imagination. But that doesn't mean the question is pointless. Quite the opposite. Asking what nothing is helps us understand what something really means. It's in the contrast that clarity emerges, or at least a kind of peaceful confusion. And as we'll see when we explore the origin of the universe, nothing may not be the end of the line, but the beginning of a very strange road. So, let's keep floating gently through the questions. There's a lot of nothing left to uncover. The big beginning, unraveling the Big Bang. Let's take a gentle step forward, or perhaps backward, depending on how you think about time. We're going to take a calm stroll through the history of, well, everything. But don't worry, you won't need a time machine or a seatbelt. Just a quiet mind, a comfortable pillow, and perhaps a sense of cosmic wonder. Tonight, we're visiting the moment the universe began, or at least the moment our current understanding says it did. This is the story of the Big Bang. Not a loud explosion in space, despite the dramatic name, but a gentle unraveling of space itself. A moment so strange that it gave birth to not only everything we see, but the very space and time in which we see it. Imagine you're standing in the deepest corner of space, far from any stars or galaxies. There's no sound, no breeze, just the soft hum of distant starlight and the feeling of cosmic stillness. That stillness, though, hides a secret. Everything, all the planets, stars, galaxies, and even the emptiness between them, is moving apart. Slowly, gently, and inevitably, space itself is stretching. This idea that the concept that the universe is expanding is a cornerstone of modern cosmology, supported by a wealth of observational evidence. This expansion is not like an explosion spreading matter into pre-existing space. Rather, it is the expansion of space itself, carrying galaxies along with it. One of the most compelling pieces of evidence for an expanding universe comes from the observation of redshift. In the early 20th century, astronomer Edwin Hubble discovered that the light from distant galaxies is shifted towards the red end of the spectrum, a phenomenon known as redshift. This redshift is interpreted as a Doppler effect, indicating that these galaxies are moving away from us. Furthermore, Hubble observed that the farther a galaxy is, the faster it appears to be receding, a relationship now known as Hubble's law. This linear relationship strongly suggests a uniform expansion of the universe. The expansion also has profound implications for the origin and ultimate fate of the cosmos. If the universe is expanding now, it must have been smaller and denser in the past. Tracing this expansion backward in time leads to the Big Bang theory, which postulates that the universe originated from an extremely hot, dense state approximately 8 billion years ago. The Big Bang theory is further supported by the discovery of the cosmic microwave background radiation, CMB, which is considered the afterglow of this initial hot phase. The rate of expansion is not constant. Observations of distant supernova have revealed that the expansion of the universe is accelerating. This acceleration is attributed to a mysterious force called dark energy, which is thought to make up a significant portion of the universe's energy density. While the exact nature of dark energy remains one of the greatest unsolved mysteries in physics, its existence is crucial for understanding the current and future evolution of the universe. The expansion of the universe raises intriguing questions about its ultimate fate. If the expansion continues indefinitely and accelerates, galaxies will eventually become so far apart that they will no longer be visible to one another, leading to a big freeze or heat death scenario where the universe becomes cold, dark, and empty. Alternatively, if the expansion were to slow down or even reverse, the universe could eventually contract in a big crunch, collapsing back into a hot, dense state. Current evidence, however, points towards an ever-accelerating expansion. In summary, the expanding universe is a dynamic and evolving entity, constantly stretching and thinning the fabric of space-time. This fundamental concept, backed by robust observational data, continues to drive cutting-edge research in cosmology, pushing the boundaries of our understanding of the cosmos and our place within it. The cosmic microwave background CMB radiation is a faint glow of light that fills the universe, an echo of the Big Bang. It is the oldest light we can observe, originating about 380 years after the Big Bang, when the universe had cooled enough for protons and electrons to combine and form neutral hydrogen atoms. This event, known as recombination, made the universe transparent to light, allowing photons to travel freely. These photons, stretched by the expansion of the universe, are what we detect today as microwaves. The CMB is remarkably uniform across the sky, with tiny temperature fluctuations on the order of parts per million. These anisotropies are incredibly important because they represent the initial density variations in the early universe, the seeds from which all the structures we see today, galaxies, clusters of galaxies, and the cosmic web, eventually grew. Studying these fluctuations provides crucial information about the universe's age, composition, geometry, and evolution. Groundbreaking observations by missions like COBE, WMAP, and Planck have precisely measured the CMB properties, confirming the Big Bang theory and providing strong evidence for inflation, a period of rapid expansion in the very early universe. The CMB also offers insights into dark matter and dark energy, mysterious components that dominate the universe's mass and energy content. Its existence and characteristics are fundamental pillars of modern cosmology, continually refined by ongoing research and new observational data. Science plays a crucial role in shaping and informing philosophical thought. It provides empirical data, theories, and methodologies that can either support, challenge, or even redefine existing philosophical concepts. For instance, advancements in neuroscience offer insights into consciousness, free will, and the nature of the mind, directly impacting philosophical debates in metaphysics and ethics. Similarly, discoveries in physics, such as quantum mechanics and relativity, have profound implications for our understanding of reality, space, time, and causality, compelling philosophers to re-evaluate traditional ontological and epistemological frameworks. The scientific method itself, with its emphasis on observation, experimentation, and critical analysis, serves as a powerful tool for philosophical inquiry, encouraging a more rigorous, evidence-based approach to complex philosophical questions. In essence, science acts as a dynamic source of new information and perspectives that continually enrich and evolve the landscape of philosophical discourse. Philosophy plays a pivotal role in shaping the direction and methodology of scientific inquiry. It provides the foundational principles, assumptions, and conceptual frameworks within which scientific theories are developed and evaluated. Without philosophical underpinnings, science would lack a coherent structure and a basis for understanding the nature of knowledge itself. One key aspect of philosophy's guidance is in defining the epistemological boundaries of science. Philosophy of science, for instance, delves into questions about what constitutes scientific knowledge, how it is acquired, and what criteria are used to validate or falsify scientific claims. This includes debates about the nature of scientific truth, the role of observation and experimentation, and the limits of empirical evidence. For example, Philosophical discussions around realism versus anti-realism in science directly influence how scientists interpret their theories, whether they believe theories literally describe an independent reality or are merely useful instruments for prediction and control. Furthermore, philosophy contributes to the methodological principles adopted by scientists. The development of the scientific method, with its emphasis on observation, hypothesis formation, experimentation, and logical inference, is deeply rooted in philosophical traditions, particularly empiricism and rationalism. Philosophers like Francis Bacon emphasized inductive reasoning and systematic observation, while others like Karl Popper introduced the concept of falsifiability as a demarcation criterion for scientific theories. These philosophical ideas have profoundly influenced how scientific research is conducted and how results are interpreted. Philosophy also informs the ethical considerations that guide scientific research. As scientific advancements gain increasing power to impact society and the environment, philosophical ethics provides a framework for addressing questions of responsibility, accountability, and moral implications of scientific discoveries and applications. Bioethics, environmental ethics, and the ethics of artificial intelligence are burgeoning fields that bridge philosophy and science, ensuring that scientific progress aligns with societal values and promotes human well-being. Moreover, philosophy helps to clarify the conceptual foundations of scientific theories. Many fundamental scientific concepts, such as causality, space, time, and consciousness, have deep philosophical roots and are subject to ongoing philosophical scrutiny. For instance, the philosophical debate on determinism versus free will has implications for fields ranging from physics to neuroscience. By critically examining these concepts, philosophy helps scientists to refine their understanding and to avoid conceptual ambiguities. Finally, philosophy contributes to the interpretative frameworks through which scientific findings are understood and integrated into a broader worldview. Science often generates data, but it is philosophy that helps to make sense of that data in terms of its implications for human existence, the nature of reality, and our place in the universe. Cosmology, for example, raises profound philosophical questions about the origins and ultimate fate of the cosmos, connecting scientific theories with metaphysical inquiries. Interpretative frameworks. Navigating meaning and understanding interpretative frameworks serve as essential lenses through which we perceive, analyze, and comprehend information, events, and human experiences. They are not merely tools for understanding, but rather foundational structures that shape our perceptions, influence our judgments, and guide our interpretations. These frameworks encompass a wide array of theoretical perspectives, methodological approaches, and conceptual models, each offering a distinct way of making sense of the complexities of the world. The nature of interpretative frameworks at their core, interpretative frameworks provide a systematic approach to extracting meaning from data, texts, behaviors, and social phenomena. They operate on the premise that meaning is not inherent or objective, but rather constructed through processes of interpretation. This construction is influenced by a multitude of factors, including epistemological assumptions, underlying beliefs about the nature of knowledge and how it can be acquired. For example, some frameworks might prioritize empirical observation, while others emphasize subjective experience. Ontological positions, views on the nature of reality itself. Is reality a fixed, external entity, or is it socially constructed and fluid? Theoretical lenses, specific theories e.g., feminism, post-structuralism, psychoanalysis that offer conceptual tools for analyzing and understanding particular aspects of reality. Methodological approaches. The specific research methods and techniques employed to gather and analyze information, e.g., ethnography, discourse analysis, hermeneutics, contextual factors, the historical, cultural, social, and political contexts in which an interpretation is being made. The role and significance interpretative frameworks play a crucial role in various disciplines and fields of inquiry, including social sciences, understanding human behavior, social structures, cultural practices, and power dynamics. For example, a Marxist framework might interpret social phenomena through the lens of class struggle, while a symbolic interactionist framework would focus on the meanings people assign to their interactions, humanities, analyzing literature, art, philosophy, and history. Hermeneutics, for instance, provides a framework for understanding the meaning of texts, while art criticism employs various frameworks to interpret aesthetic expressions. Law, interpreting legal statutes, precedents, and contracts. Legal interpretivism, for example, explores how judges and lawyers assign meaning to legal texts in specific contexts. Education, understanding learning processes, curriculum design, and pedagogical practices. Constructivist frameworks, for example, emphasize the active role of learners in constructing their own knowledge. Business and management, making sense of organizational culture, consumer behavior, and market trends. Different frameworks can be used to interpret qualitative data from customer feedback or employee interviews. Types and examples. Interpretative frameworks can be broadly categorized, though there is often overlap and interconnections between them. Hermeneutics focuses on the theory of interpretation, particularly of texts. It emphasizes the cyclical process of understanding parts in relation to the whole, and the role of the interpreter's pre-understanding. Phenomenology aims to understand lived experiences and consciousness from the subjective perspective of individuals. It seeks to describe phenomena as they appear to consciousness, free from theoretical assumptions. Symbolic interactionism examines how individuals create meaning through their interactions with others and through the interpretation of symbols. It emphasizes the social construction of reality. Discourse analysis analyzes language in use to understand how meaning is constructed and how power relations are embedded in communication. It examines written, spoken, and visual forms of discourse. Feminist frameworks interpret phenomena through the lens of gender, power, and social inequality. They challenge dominant patriarchal interpretations and seek to give voice to marginalized perspectives. Post-structuralism questions the notion of fixed meaning and universal truths, emphasizing the instability of language and the multiplicity of interpretations. It often deconstructs established narratives and power structures. Critical theory seeks to critique and transform society by uncovering power imbalances, ideologies, and forms of oppression. It aims to empower marginalized groups and promote social justice. Grounded theory, a systematic methodology for developing theory from data. It involves iterative processes of data collection, coding, and analysis to generate theoretical concepts grounded in empirical observations. Challenges and considerations. While interpretative frameworks offer invaluable tools for understanding, their application also presents certain challenges. Subjectivity and bias. The interpreter's own background, experiences, and biases can influence the interpretation. Reflexivity, the process of critically examining one's own role in the research process, is crucial. Relativism, the recognition that multiple valid interpretations can exist, raises questions about objective truth. However, most interpretative approaches do not advocate for complete relativism. but rather for a nuanced understanding of different perspectives. Rigor and validity, ensuring the trustworthiness and credibility of interpretations, is vital. This often involves techniques like triangulation, using multiple sources of data or methods, member checking, verifying interpretations with participants, and detailed methodological descriptions. Complexity. Applying interpretative frameworks often requires a deep understanding of complex theoretical concepts and sophisticated analytical skills. In conclusion, interpretative frameworks are indispensable for navigating the multifaceted nature of meaning and understanding. They provide a structured approach to analyzing diverse forms of information, revealing hidden meanings, and generating new insights. By consciously selecting and applying appropriate frameworks, researchers and thinkers can deepen their comprehension of the world and contribute to richer, more nuanced forms of knowledge. In essence, philosophy acts as the underlying architecture upon which the edifice of science is built. It provides the intellectual tools, critical perspectives, and ethical compass that enable science to not only advance knowledge, but also to do so responsibly and meaningfully. Without philosophical guidance, science would be a collection of disconnected facts, lacking the depth, coherence, and ethical grounding necessary to truly serve humanity.